Today, we want to look at the next big thing, and the next big thing is going to be sequences, series, and power series. If you would recall, calculus is about infinity. Studying calculus is about making rigorous the idea of infinity. We talk about the derivative as a slope of the tangent line at a point, and we create that by looking at a secant line and making the points infinitely close together. We talk about area by dividing a rectangle, by dividing a region up into a bunch of rectangles, and then making the rectangles infinitely thin. So we're dealing with questions of infinity, and that's what we're going to continue doing in this topic. Sequences, series, and power series. So infinity involved in each of these things. Infinity is involved in each of these things, but in a slightly different way. That's why it fits into this in calculus. So here's how we want to think of each of these three things. Sequences a sequence is just a list, an infinite list, hopefully with some pattern to it. We'll talk about what we need out of sequences soon. A series is a sum. Here's where we're adding up an infinite number of terms. And a power series is like a polynomial, but with infinite degree. So we want to think of a power series first and foremost as a function. And the form of the function is a polynomial, but with infinite degree. Now, I realize that having an infinite degree means it's no longer a polynomial. Polynomial has to stop somewhere. But the form of the power series is going to be that of a polynomial. And we need each of these things in turn so we can get to the power series business. Always remember that we're looking at calculus, and calculus is about infinity. So a sequence is an infinitely long list. A series is an infinitely long sum. It's the sum of an infinite number of terms. And a power series is polynomial, but with infinite degree. So it's still all about infinity. Calculus is about infinity. Let's talk about how each of these three things are put together. The typical order is to talk about sequences, then use that to talk about series, and then use that to talk about power series, which I think is backwards. I think we need to start with the last thing, even though it depends on the first two, because that's the one that we care about more than the others. So let's start with a power series. So once again, we're going to think of a power series as an infinitely long polynomial of infinite degree. It's a function. We get to plug things into it. There's going to be inputs and outputs for our function, and the form of the function will be a polynomial, but with infinite degree. So the form is going to be a polynomial with infinite degree. So it will look something like this. We'll have a sum as I goes from 0 to infinity. And we're just going to have some coefficients which I'm going to label C sub n, and then we'll have powers of x minus a to the n. So we're going to start off with a constant term, C0, then a first degree term, plus C1 times x minus a, and then a second degree term, plus C2 times x minus a squared. And then this just pattern goes on forever. So we can plug things into the function. We can plug in values of x, and then the outputs, when we plug in a value of x, will be a series, an infinite sum of constants. So when we plug a value of x, when we substitute a value of x into a power series, we end up with a series, which is just a sum of constants. So a series is a sum with an infinite number of terms. So a series will just be a sum of an infinite number of terms. So something like a sum, as I goes from 0 to infinity, of just some constants, a sub n. So a0 plus a1 plus a2 plus a3, and so on. So our goal is to think of power series as some new kind of function. But we have to study series so that, because when we substitute values into a power series, the output is a series. So the input, we input a real number into a power series, and the output is going to be a series. Here's what we care about when we're looking at a series. When we're looking at a series, we care if the series converges or diverges. We care if this sum is finite or infinite. For a series, we want to know if the series is infinite or finite. So for a series, we want to know if the series is convergent. This is when the sum is finite. Or divergent. This is when the sum is infinite. So when we have a power series, which is a function, we plug something into the function, the output is a series, and we want to know if that series is convergent or divergent. We want to know if that series, which is just a sum of an infinite number of terms, is going to be finite or infinite. We want to know if when we plug that number into plug x into a power series, do we get something that makes sense? Do we get something finite or do we get something infinite? Just like we care about the domain and range of a function. When we have the function 1 over x, we can plug in any real number that isn't 0. because when we plug in 0, we don't get a value. Same thing happens with power series. It's like a function. What do we plug in? What can we plug into the function so that we get a finite value when in the series that results? And we refer to that as a convergent series or a divergent series. DVD bonus material, which will show up later anyway. But looking into the future, there are 2 kinds of convergence. So to add on to this, 2 kinds of convergence. There's absolute and conditional. Here's what it means when we talk about series from a student standpoint. We do want to understand the concept of the series, but notice that when I hand you a series, I've given you a multiple choice question. Convergent or divergent, and if it's convergent, absolute or conditional. So there's really 3 choices: absolute convergence, conditional convergence, or divergence. That's what we're talking about with a series. So let's stop here and look at an example of a series. So for example, here's a series. Oops, I used an N here and an N here, and I started I for index. Let's change our index to an N. You know, I was still thinking of indexing things from with I's because we were just in the slicing chapter. All right, so let's write a series, and I'm just going to say N. So what this series will look like is I plug in 1, and then I plug in 2, and then I plug in 3, and I add these things all up forever. Sometimes we don't need any fancy techniques. We can just look at a series and say, this is going to diverge. This is a divergent series. It represents an infinite sum. So this series diverges. It represents an infinite sum. Let's write another one. Let's start off with 1. Let me start over again. Let's say the sum as n goes from 1 to infinity of 3 to the minus n. Let's just write down the terms of, this is not the series I wanted either. This is why I shouldn't do this coming right out of spring break. Coming right out of spring break, I should start off with something like, here is how we multiply polynomials, although I'm not really sure that I could do that right now either. Let me see if I can actually write down the example that I wanted to do. N is going to go from 1 to infinity. At least I got the indexing sorted out. And I want actually 3 times 10 to the negative n. Let's see if this is going to do what I wanted to do. So we're going to plug n equals 1 into the expression, and then 2, and then 3, and then 4, and then see what the series is. We're going to add up all those terms. So we get 3 times 10 to the negative 1, so 0.3. And then 3 times 10 to the negative 2, 0.03. And then 3 times 10 to the negative 3, 0.003. And we're going to do this forever. So we have an expression. We're plugging in all the values of the integer values of n from 1 to infinity, and then we're adding up all those terms. We have an infinite number of terms. This is one that we recognize. So we got 0.3 plus 0.03 plus 0.003. If we do this forever, we can see that the sum is going to be 1/3. So we would say that this series converges because the sum is finite. Moreover, not only is the sum finite, we know that the sum is finite because we know what the sum is. We don't always get to know that. Sometimes we're looking at a series and we can definitely say that this series converges. It has a finite sum. And then the natural question after that is like, oh, well, what is the sum? And you're like, oh, I don't know. It's some finite number. Because from certain standpoints, finite is all we really care about. At least with absolute convergence, when I say it is finite and it has a sum, I can say it has a sum. With conditional convergence, it's more fun because someone will be like, oh, what is the sum of this conditionally convergent series? And you can be like, what do you want it to be? And then you just set about rearranging the terms to make that sum. Addition gets really weird when there's an infinite number of terms. That's what I'm saying. Any questions? The reason that I bring this up is right away is that when we're looking at a series, I'm saying that there's an infinite number of terms and we're adding them all up, and we want to know if that sum is finite. And so the natural question would be, how can we have a finite sum if there's an infinite number of terms? And I just want to point out the one that you already know. Here's a sum with an infinite number of terms, and you know that the sum is only 1/3. So that's the reason that I do this one. Any questions? So our goal is to look at power series, even though that's the last section in this chapter. Our goal is to look at power series because we want to use power series to model functions. But to understand power series, we got to understand what a power series, how a power series works. It's like a function. When we plug stuff into the function, we end up with a series. So now we have to understand series. So when we plug stuff into the power series, do we get a convergent series, or do we get a divergent series? In a certain sense, the things that we can plug into the power series and come up with a convergent series is like the domain of the power series. If you'll allow me to be really loose with the language, which you all are very gracious in allowing me to be pretty loose with my language, even though math is a very rigorous language. Or when we plug something into the power series, do we get a divergent series? In which case we would say that value is not in the domain of this function. Because when we plug stuff in, we try to plug those values in, it doesn't make sense. So then the goal just becomes looking at series and determining quickly if they converge or diverge. Our goal when we're looking at series is to determine quickly whether they converge or diverge. So raises the question, there was something at the beginning. It was called sequences. You said we're going to do this backwards, and we're right in the middle. So what do sequences have to do with it? A sequence is just a list. It's just a list with an infinite number of terms. A sequence is just a list with an infinite number of terms. So we're not adding things up. So to write a sequence, we'll just write some expression Sn, and then just say for n greater than or equal to 1. Can't use the equal sign because I'm looking at a new thing, but this would just be a list. S1, S2, S3, S4. We're not adding them up. We're just listing a bunch of things. So for example, I could say Sn is n squared for n greater than or equal to 1. I'll just plug in 1, 1 squared, 2 squared, 3 squared, 4 squared, and so on. We're just making a list. We're not adding them up. We're just listing things. Another example of a sequence. Let's suppose that Sn is 3 plus 2n over 7 plus 5n for n greater than or equal to 0. It's math. We can start the counting at 0. We can start the counting at 1, whatever happens to be convenient for us at the time. So this list of numbers will just start off with n equals 0 of 3/7. And then we'll plug in 1. 3 plus 2 is 5, and 7 plus 5 is something. So 5/12. And then when n is 2, we get 3 plus 2 times 2, or 4. So 3 and 4 is 7. And then 12 plus another 5 is 17. So here's our list: 3, 5, 7, 9, 22s, 11 27s, and so on. We're just creating a list. We're not trying to add all these values up. We're just listing them out. In one of the few terrible crossover events from mathematics, we use the same language, converges or diverges, when we apply it to sequences. But it means something different because we're talking about a different object. So a sequence converges if the terms have a limit. So this sequence n squared, this sequence we say diverges because the terms do not have a limit. This sequence diverges. The terms do not have a limit. The terms do not have a limit, so that sequence diverges. The second example, if we look at the limit as n goes to infinity of 3 plus 2n over 7 plus 5n, when n is extraordinarily large, 3 and 7 don't matter. All that matters is 2n and 5n. And 2 times a lot divided by 5 times that same a lot will just be 2/5. So we would say that this sequence converges. And since we know what the limit is, 2/5, we would say converges to 2/5. So we talk about a sequence converges or diverges, and we talk about a series converges or diverges. And we're using converges or diverges in a slightly different context depending on what we're talking about. The interesting thing to note here is that we're still talking about infinity, but instead of things becoming infinitely close together like they were in derivatives and integrals, things are keeping the same distance apart. We're not looking at continuous inputs. We're looking at a bunch of continuous outputs from a certain point of view. Notice that we're plugging in integers, but we're plugging in an infinite number of integers. The 1 and the 4, the values that we're plugging into the n squared aren't getting closer together. We're not changing some delta x and plugging that into the function. Delta x, or the delta n in this case, is fixed at 1. So we're just plugging in integers. So that's the way infinity is getting expressed in sequences, series, and power series. So what do sequences tell us about series? We know what series, what we need to know about series so that we can understand power series, which is kind of the goal. So how do sequences inform us about series? We can use a sequence to tell us if a series converges. We use a sequence of partial sums to determine if a series converges. So we can use a special sequence called the sequence of partial sums and that will tell us if a series converges. So let's suppose that we have a series. We'd say that a series converges. Well, this is not really an example. I'm just going to write this out. We'll say that a series converges if its sequence of partial sums converges. The sequence of partial sums is going to be a list. The first term in the sequence of partial sums is just a0. The next term in the sequence of partial sums is a0 plus a1. The next term in the sequence of partial sums is a0 plus a1 plus a2. Then the next one Wait for it. So what we're doing is making a sequence. We're just making a list of partial sums. Start with the first term, then the first two terms, then three terms, then four terms. The way we want to think about this is us just trying to find the sum of the series by adding up a bunch of terms, but looking at the sum as we go and seeing, is this headed somewhere? So note, this is a brute force thing. We're just finding the sum of the series. We're adding up 1,000 terms, and then we're adding up 10,000 terms and seeing, is this leveling off somewhere? Is this headed somewhere? Or is this sequence going to diverge? Ultimately, this is not how we're actually going to determine if a series converges or diverges. We're just going to determine if a series converges or diverges by looking at it. Well, we got to start somewhere. And it's nice to know that when we're looking at an infinite number of terms, deciding if their sum is finite or infinite, if we need to, we have a brute force approach. Anytime you have a brute force approach in a world of massive amounts of computing power, you should feel at least a little bit comforted. Computer engineers will try to build us some faster computers so we can brute force some more numbers. Computer scientists will try to write us some more efficient programs. Engineers will try to build us better conductors so that our computers will go faster, and mathematicians will constantly be trying to find better ways of doing things. And physicists will tell us when the engineers are just asking for things that are physically impossible. Similarly, chemists. You know what I mean? All fits together. Then the biologists will be able to tell us, you know, when the computer runs this way, it's going to be bad for the living organisms around it. And then the biological engineers, like doctors, will say, yep, here's all the cancer that's being caused by your computer. And then we'll all say, but it's fast. And I can run Fortnite at 1,000 FPS. Meanwhile, the amount of energy required to run that computer is like the amount of energy required to run like the state of Oklahoma or something. I don't know. I don't know how this works. I'm just the math guy. Any questions? All right, so the next big thing that we're looking at, it's all in chapter 9, and we pretty much did all of chapter 9 just right now, just in the last 40 minutes. This is chapter 9 in a nutshell. Sequences, series, power series. The way we actually care about it is power series is the big deal. Power series is when we're looking at functions. We're trying to express functions as infinite polynomials. To do that, we need to understand sequences. Sorry, we need to understand series, because when we plug things into a power series, we end up with a series, and we have to know if that series is finite or infinite. Does the series converge or diverge? One way we can determine if a series converges or diverges is by looking at a sequence of partial sums. All right, so that's where we're at. That's what we want to start working on. Running in the background is still all the applications of integration and all the slicing things. That's also very simple. Slice where things are constant, and then just slice more often. Infinity, when we're talking about derivatives and integrals, infinity is just squishing this way and making things infinitely thin and infinitely close together. Sequences, series, power series is just about infinity keeping the same distance apart, integers as integer distance apart, but it's a discrete infinity rather than a continuous infinity. Kind of should have seen this coming. Discrete versus continuous, both need an infinity. All right, that's going to do it for today. I will see y'all on tomorrow, and we'll start talking more details about series. All right, everybody have a good day. I'll see y'all on tomorrow, and thanks for playing.